Hey, welcome back to Calculus. In this video lecture, we're going to take a look at section 6.3, where we're going to add the derivatives of the six trigonometric functions to our differentiation repertoire. So you can see the objectives of the lecture there in front of you. We're going to derive, and we're going to do it by definition, the derivatives of sine and cosine. All right, and then once we have those, we're going to use the quotient rule to differentiate the tangent, the cotangent, the secant, and the cosecant, because as you remember from trigonometry, those other trigonometric functions, tangent, cotangent, secant, and cosecant, they're all defined in terms of sine and cosine, certain ratios. All right, so that's going to be our work. I won't derive all of this stuff in this lecture. I'm going to farm some of it out to you in your homework and activities, but I'll definitely try to do enough to give you the spirit of how the calculations work. You can see I've drawn a little picture here, maybe just as some eye candy, but also to remind you how we're thinking about sine and cosine here. I mean, they're certainly useful in right triangle trigonometry, but in particular, in this lecture, in this class, whenever I'm speaking about the trigonometric functions, I always measure their angles in radians. So I always think of these things as functions of a real number that's measured in radians, never in degrees. And let me just remind you what the sine and cosine are. If you take an angle theta, a positive number, say in this picture, and you, from the standard position, that is from the positive x-axis, you measure an angle theta. Positive angles are measured counterclockwise, mathematically positive, sometimes people call it. Then as soon as you pick that angle, theta, it determines the point on the unit circle. As soon as you decide how much to open that little wedge, where the terminal angle of the wedge lands is determined by the angle. So those two coordinates there, x and y, are therefore functions of the angle, and those functions' names are cosine and sine, respectively. So the cosine and the sine are the x and y coordinates of a point on the unit circle that's defined by the angle theta in the convention that we measure it from the positive x-axis with positive angles being counterclockwise. All right, so if you need to review some trigonometry, there's some stuff on the Canvas page linked to the Khan Academy, or come to one of my office hours and we can scour around, talk to each other about trigonometry and scour around and find some resources for you. But right now, I'm just going to assume that we're comfortable with these functions, and I want to motivate what the derivative of sine. I actually want to try to see if we could just guess it. So I took this picture from your book. It's a lovely picture. So drawn on the top graph there is a picture of the sine function. The angle is being called x. It's okay. It doesn't matter what we call the angle. We can call it x. And the author is sketching the graph of the derivative below it using ideas that we talked about when we were talking about the derivative as a function back in chapter 2. So let me just kind of bring your attention to some of these places. Whenever you're thinking about sketching the graph of a derivative, the first thing you want to do is look for these horizontal tangent lines of your function. Horizontal tangent lines kind of leap out at you. The sine is going to have infinitely many of them. They're going to happen at points like pi over 2, 3 pi over 2, 5 pi over 2, and so on. So at any one of those horizontal tangent lines, notice that the corresponding points on the derivative are 0, because the graph of the derivative down here, its y coordinates are the slopes, right? The y coordinates on this derivative graph are the slopes of the graph above. So let's just pick a couple spots here, say between this horizontal tangent line and this one at pi over 2 and 3 pi over 2. Reading the graph left to right, we can see that all the tangent slopes are negative, and the most negative one happens at pi there. We don't know the value. There's no scale on the y-axis here, but that's consistent with this picture. Between these two zeros, all these tangent slopes are negative, and the most negative one, the lowest y-coordinate down here, happens at pi. All right, and so on. So you can kind of look at this picture, stop the video for a second, and convince yourself that, yeah, that purple graph on the bottom, its y-coordinates are consistent with the slope information on the graph on the top. It has the right shape to be the derivative. And there's some kind of cool things we can notice about this. Sine, you know, is a periodic function. Every 2 pi units, the sine function basically repeats that part of its graph. Well, the derivative of a periodic function is going to be periodic, because if the y values and how they're related are changing in the same way every time you go through the period, well, so will the slopes. So we already know the derivative of the sine function is some periodic function. It's got the same period, 2 pi. Its maximums are at 0 and 2 pi. The minimum is at pi. It's all very consistent with another one of the trigonometric functions. All right. So I'm just going to kind of plant that seed here, or maybe we should say it. Can you pause the video? Do you have a guess? What function do you think that this derivative down here is? What is the function down here? It looks like y prime. This is my guess. I want to be honest. I haven't computed anything, but it looks like that it's just the cosine function. It looks like the derivative of the sine wave is the cosine wave, which is kind of interesting. It's in and of itself, if you think about it in terms of the unit circle definition. Okay, so to see if that guess is correct, we're going to go back to first principles. We're going to derive the derivative of sine from the limit definition. To do it, we're going to need a couple. We're going to need a couple of facts, some preliminary results. So I decided just to kind of list them out here instead of building them in as we go. I'll just kind of put them out there. So a couple of these preliminary facts that we're going to need are going to be these things that are usually called addition formulas for sine and cosine. You can see how they're going to come up in our work, because when we're looking at the derivative, of course, we're going to be looking at the sine of x plus h minus the sine of x. So these things, these addition formulas, you can look them up in your trigonometry book, or they're also in the back of our book in the reference section, but these are usually called the addition formulas for sine and cosine. I'm not going to derive them here. I'm just going to be using them. Okay, and in particular, we're going to do the derivative of sine from scratch. So I'm going to be using that first one. I'm going to leave the second one as an exercise to you. So those are addition formulas from trigonometry. Some other preliminary facts that we're going to need to use are a couple of special limits. There's a couple of special limits. This limit, when we were back looking at limits in chapter 2, we did it by looking at a table and a graph. So that's how I'm going to leave it here. There's a beautiful geometric argument in your book that uses the squeeze theorem. If you want to talk to me about that in an office hour, we can certainly do it. But to keep this video short, I'm just going to say, well, we investigated this limit with tables and graphs, and we saw that it was equal to 1. We never did this one, I don't think, with tables and graphs, and I'm just going to assign it as an informal exercise to you to plot the function cosine of h minus 1 over h and look at what its values are doing near the origin. Or get out a spreadsheet and look at its values, look at a table of values when h is very small. If you're going to do that with tables, you make sure that your trig functions are being evaluated in radians. I don't want to harp on it too much, but if you are measuring this angle in degrees, then these limit statements that I'm writing down are true. So they have to be, the h variable has to be measured in radians, okay? All right, so using those preliminary results, you can see I kind of revealed a little bit too much down there. I want to start the derivative computation of the sine. Right, so looking at the limit definition, we'll just start it off. The limit definition of derivative is we take the limit as h goes to 0 of the function's value at x plus h minus the function's value at x divided by h. And the first thing I'm going to do, the first algebraic move I'm going to do is I'm going to replace this sine of x plus h with what it equals in terms of this addition formula. So I'm going to take that sine of x plus h in the numerator and replace it with those two terms, sine of x times cosine of h plus sine of h times cosine of x. So I wrote this out so that we don't have to go so slow through the computation. I'll just reveal it. So that's what I'm doing first. That sine of x plus h, I'm just replacing with those terms. That's the addition formula for the sine function. All right. And now I'm going to do a little bit of algebra. Let me show you just by sort of highlighting or underlining or somehow what I'm doing. I see in this numerator a term that has a sine x in it, sine x times cosine h. There's another term that has a sine x in it. So I'm going to factor sine x out of those two terms. That's where it goes right there. And what would that sine x be times? It would be times, well, cosine h minus 1. Yeah, so that's all I did. And really, that's the only algebra I did, although I did rewrite the order here of these guys. Sine times cosine, I swapped their order. But multiplication, the order doesn't matter which way we write them, all right? So that'll get us down to that line. And then I'm using limit properties. Now I'm going to use limit properties because, well, I'm going to divide this h into the two terms in the numerator. And I'm going to write that the limit of a sum is the sum of the limits. So that's why I've got two limits here. And then the last little thing I did is that the sine x doesn't depend on h, so it can come through the limit. Yeah, sine of x doesn't depend on h, it can come through the limit. So does cosine. Cosine doesn't depend on h, so it can come through the limit. All right, and now looking at these things, well, I've got the sine of x times, what is that thing? That limit is that one of the preliminary limits that we wrote up there, cosine of h minus 1 over h goes to 0. This is the other one, sine of h over h as h goes to 0 goes to 1. So I'm just replacing those things with 0 and 1 respectively. And well, sine times 0 is 0 and cosine times 1 is 1. And so there you go. The derivative of sine, we finally arrived at it, is cosine. So let me just sort of put that there. You can pause the video and jot this stuff down. I hope that computation makes sense. You might need to do it a little slower than what I'm talking, but I'm just kind of walking through stuff that I've already written through. But you can rewind and go back and look and make sure that my algebraic computations are valid. All right, so that's the main result. The derivative of sine is cosine. I'm not going to go through it, but you can. Similarly, it's one of the most dangerous words in mathematics. Similarly, you can show that the derivative of cosine is minus sine. So I hope you take this challenge that you have to use the addition formula for cosine. The same two special limits will come up, and after algebraically manipulating that, I kind of gave you a template you can try. You should be able to derive that the derivative of cosine is the opposite of sine. It's the negative sign, the opposite of the sine function. All right, so there's the two main trig derivatives. These are things you're going to want to practice enough to kind of put them into your memory so that you can access that information easily. The derivative of sine is cosine. The derivative of cosine is the opposite of sine. But now we don't have to use the limit definition of derivative to do any of the other four trig functions because of their relationships and ratios. So I'd like to compute out an example. I didn't write it out ahead of time, so we can write it together. I want to take the derivative of the tangent function with you. All right, I don't have to do this from first principles because the tangent function, you remember from trigonometry, is the ratio of the sine function to the cosine function. Tangent is, by definition, sine over cosine. Well, we know the derivative of sine, we know the derivative of cosine, and we know the quotient rule. So we'll just use it. We're going to use the quotient rule to derive the derivative of tangent. We don't have to go back to first principles. Sine and cosine are like the fundamental building blocks of all things trigonometry. If you know how things work for sine and cosine, you know how things are going to work for any trigonometric function. Okay, so quotient rule. Hopefully you've practiced it a lot since we talked about it last time in these videos, but here we go. What do you do with the quotient rule? Well, it's a fraction, and you have to square the denominator. For trig functions, we write their exponents in that kind of peculiar place, so this is just the way to write cosine times cosine. And then what do? You take the derivative, or sorry, the denominator undifferentiated, and you have to multiply it by the derivative differentiated. Maybe you don't write this step anymore. It's okay. You can start skipping that step, and then you have to differentiate the denominator and multiply it by the numerator undifferentiated. All right? So let's see if we can't simplify this a little bit. We've got cosine, derivative of sine, we just derived is cosine. And then the derivative of cosine, we just said is minus sine. We didn't derive it, but I'm hoping you will. Take my word for it for right now. It's all divided by cosine squared. And can we continue to simplify this a little bit? It looks like it does. We've got cosine times cosine in the top, so that's a cosine squared. The two minus signs make a plus, and that's a sine squared. And in some sense, this is my answer. I don't have to keep manipulating this thing, but maybe you do recognize it's a very important trigonometric identity that no matter what the angle x is, you know what the sine and cosine squared of x always adds up to for any x? They always add up to 1. Yeah, very important trigonometric identity. I usually tell people that's the only trigonometric identity that I actually feel like I know. I've burned it into my brain. I never have to look it up. Sine squared plus cosine squared is 1. So that's a nice simplification. If we write that numerator as 1 over cosine squared, very nice. And that's a nice answer. But if you look at a table in a book or somewhere, they're not going to say the derivative of tangent is 1 over cosine squared. They're going to write it as secant squared. Yeah, so more trigonometric stuff. The reciprocal of the cosine function is the secant function. So to summarize our long computation, if I can try to squeeze it back on the screen, when we were trying to take the derivative of the tangent function, we got the square of the secant function. All right, so there's 3 of the 6 trig functions, and I'm going to farm the other 3 out to you. I'm going to scroll down here and let us look at them while we're talking. But the other trigonometric functions, their derivatives work like this. Oh, I wish I wouldn't have done that. We've done these 3. We did the derivative of sine as cosine by definition, while I'm encouraging you to modify that computation and prove to yourself that the derivative of cosine is minus sine. We just looked at the derivative of tangent and got secant squared, but we had to use a little trig identity. It's not really an identity, but a definition there at the end. So what I'm hoping you do is you'll check these 3. The derivative of cosecant, maybe I should remind you here, cosecant is the reciprocal of the sine function. Yeah, so when you go to differentiate cosecant, swap it for 1 over sine and use the quotient rule. When you go to do secant, swap it for 1 over cosine and use the quotient rule, and cotangent is cosine over sine. So I'm going to leave these 3 to you to verify. All right, so there we are. There's the derivative of the 6 trigonometric functions. All right, let's end this video just by a couple of skill and drill practice things. I want to circle back through some old ideas, practice these new derivatives, practice product rules and quotient rules and all that stuff. So here's our first one. First example, we can enumerate it if you want to. Let's take the exponential function e to the x times sine x. You should pause this video and look at that on Desmos. It's got kind of a cool looking graph. E to the x times sine x. And then let's find its second derivative. All right, you want to find the second derivative of a function, you have to find the first derivative first. There's no shortcut from the function to the second derivative. So we're going to take f prime to begin this calculation. And then we want to simplify it as much as possible. And when we have, then we'll take the derivative of that to get f double prime. All right, it's a product rule. I've got e to the x times sine x. So the product rule is first function times derivative of second plus derivative of first function times second. That's the pattern. Maybe you're skipping that step by now. I'm going to start skipping it pretty soon because you can just, once you have that product rule pattern burned into your brain, what I'm about to write right now can be the first thing you're going to write is you'll go, well, I'm leaving e to the x alone and I'm multiplying it by the derivative of sine. It's cosine. And then I have to add the derivative of e to the x. Well, that's e to the x times sine. Right? That simplifies kind of nicely. And I think I do want to simplify it because I'm going to differentiate this thing in a second. And it's easier to differentiate if it's in a simpler form. So there's my first derivative. Yeah, and I'm just going to draw a little red box around it here as we're talking because when I go to compute the second derivative, I'm looking here. Right? Because the second derivative is just the derivative of the first derivative. So I have to focus my attention on that's the function I'm differentiating now. I'm just finding the derivative of that function that's drawn in the red box. So let's see if I gave myself enough room to do it here. It's always a mystery for me when I make these things. So f double prime, it's also a product. It's also a product. So I'm going to write, well, it's the first function times the derivative of the second. Feel free to do that derivative on the fly if you like, but I'm going to write this just focusing on the product rule pattern. And then it's the derivative of the first function times the second. Right? Always be patient, give yourself a lot of room, write out everything neatly, and it'll make the mathematics more enjoyable and also minimize the number of errors that you make. Give yourselves a lot of room and do lots of little steps. Okay, so what do we got? E to the x times the derivative of cosine plus sine. Well, we have to use the sum rule. Differentiate term by term. The derivative of cosine is negative sine. The derivative of sine is cosine. Those are our 2 new facts. E to the x is its own derivative. It always will be and always was. Cool. And we're done. That's the second derivative. I've got a little bit more room. Let's simplify it. You can factor out an e to the x. It's common when you're doing things with exponentials that they'll stick around as factors because of their own derivatives. And then do we get any term cancellation? Well, let's see. What do we got? We've got negative sine x plus cosine x plus cosine x from the second factor plus a sine x. And so, yeah, the sine term showed up once with a minus sign, once with a plus sign. So they eliminate each other. So we can write this thing as 2 times e to the x times cosine of x if we combine those two cosine terms. All right, that is a pretty nice version of our second derivative. Much nicer than, say, this line. They're equal. I shouldn't favor one of them over the other, but if I were going to do something with this, try to find where the second derivative is 0, take the third derivative or whatever, I much prefer this last expression. It's easier to work with. Okay, cool. Let's do another one. Let's do another. This time I've got a function, it's a ratio. I wanted to practice the quotient rule with you guys. So I've got a function that's a ratio, secant x over 1 plus tangent x. And I'm trying to circle back through ideas, asking you, well, where does this thing have horizontal tangents? So maybe you should pause the video and convert that into a statement, a question about derivatives, right? When somebody's asking, when does some function have horizontal tangents? Did you stop and ask it? It's asking the question, when is f prime of x equal to 0, right? Because f prime is the tangent slope and horizontal lines have slope 0. So that's the question we're asking, is when does this thing have horizontal tangent lines? Let's switch over to Desmos real quick and just sort of see if there's an answer. I'm trying to do this to give you guys the habit of always thinking about stuff in a graph. You can always use a graph to think about a math question if it's about a function. So here I've switched over to my Desmos window, but to save us time, I've already typed our function in, secant x over 1 plus tangent x. Desmos is a good egg and it knows that x is in radians. So it's plotting this thing. And I can see, well, this is a periodic function. I'm not surprised by it. Secant x over 1 plus tangent x, because secant and tangent are both periodic. And it looks to me like there's a whole bunch of places. Desmos is even revealing them to me. I don't want to stop on them too long because I want to do it with algebra. But yeah, there's a whole infinite family of places where these things have horizontal tangent lines. Right? An infinite family of points where their tangent lines are horizontal. So we'll come back to Desmos here in a second and mouse over those again, but let's go back to our whiteboard where we can work. This takes just a little bit longer switching back because I have to politely ask my iPad to project here, but we're back. All right, so I'm asking the question, when is the derivative equal to 0? Well, we better compute that derivative. So let's do it. It's quotient rule calculation. Here we go. So f prime, using the quotient rule, I'm going to write the numerator first. So it starts off with the denominator term undifferentiated, just talking about the quotient rule pattern, times the derivative of the numerator. And then you subtract the other way around. You put the numerator undifferentiated times the derivative of the denominator. All of that has to get divided by the denominator squared. No differentiation down there. All right, so that's our quotient rule pattern. Let's see what we can do here. We got 1 plus tangent x in the numerator, not doing anything to that, but the derivative of secant, you should stop the video and go back up to the table because it's a brand new derivative for you, but I've memorized it and I'm just going to keep going. The derivative of secant is secant times tangent. That's what is written in that table up there. And then we have to subtract the secant times the derivative of 1 plus tangent. The derivative of 1 is 0 and the derivative of tangent is secant squared. That calculation we did do together above with the quotient rule. So that's all got to be divided by 1 plus tangent squared. All right, is my handwriting too messy to be able to read? Now we got to try to clean this up. Let's just check out, well, what can we do? Maybe we can do this a little smarter than just multiplying everything out. Can you see that in the numerator, there are both terms, both terms have a factor of secant in them in the numerator. So let's factor that out. This will decrease the amount of multiplication that we have to do. So I'm going to factor out secant, and then what would be left? Well, what would be left would be, maybe I can color code it. I have to multiply this tangent through the 1 plus tangent. And well, over here, I would have secant squared left. Yeah. So if we do that, if we start writing it, and if the way I'm organizing my algebra doesn't feel good, it's okay. You can organize the algebra any way you like, as long as it's algebraically correct. So tangent times 1 is tangent. Tangent times tangent is tangent squared. And then I'm going to subtract, well, I've got a secant squared down here because I've pulled out one of those secants. Okay. And well, in some sense, I'm done. This is the first derivative, but it's difficult to see when that's going to equal 0. So in order to manipulate it a little bit, to simplify it a little bit rather, I'm going to use a trig identity. This tangent squared piece, maybe you remember, maybe I'll write it off to the side here. There's a trig identity that says that if you take the square of tangent and add 1 to it, you get the square of secant. It comes from that Pythagorean identity, sine squared plus cosine squared is 1. So if you rearrange that a little bit, you could write the tangent squared. Maybe I'll do this by some erasure magic. Tangent squared is secant squared minus 1. Yeah, if I subtract 1 from both sides. So I'm going to replace this yellow highlighted tangent squared with secant squared minus 1. And when I do it, then the two secant squareds, one will have a plus sign, one has a minus sign. They eliminate each other, right? So let's see, I'm being a little bit lazy and trying to just talk you through algebra instead of writing it, but let me see how this goes down. So that tangent squared, I'm replacing it with secant squared minus 1, but the secant squared would then cancel that minus secant squared, and so I'm just going to be left with minus 1 in there. So I'm happy with this form of my derivative. I'm happy with that form of my derivative, because now I can see, when does this thing equal 0? I'm setting it equal to 0. I'm going to kind of run out of room here. I might have to shrink some stuff to write the punchline, but how can this thing equal 0? Well, a fraction is only 0 when its numerator is. Yeah. So the only way this thing can equal 0 is when its numerator is equal to 0. So I have to set secant x equal to 0, or tangent of x has to equal 1. That's the only way that that expression can equal 0. I'm going to put a little symbol there, meaning if and only if. That this equation is true if and only if those things. The denominator over here cannot contribute to the function being 0. Cannot contribute to the function being 0. It can contribute to it being undefined, but it can't make it equal to 0. Zeros only come from the numerator. And this numerator has two factors. One of those factors is secant x. So maybe that's one way the numerator could be 0. The other factor was tangent minus 1. Well, tangent minus 1 is 0 if and only if tangent is 1, right? The secant of x, secant is 1 over cosine. 1 over cosine is never 0. So there's no solutions to secant x equals 0. So they only come from here. The tangent of x is equal to 1. Yeah. And one angle in the unit circle for which tangent is 1, sine is equal to cosine, is pi over 4. It's pi over 4. But tangent is a periodic function with period pi, every pi units. So you can take that pi over 4 and add any whole number multiple of pi. So n here could be 0, plus or minus 1, plus or minus 2. So this is going to be our complete answer to the question, where does this function, secant x over 1 plus tangent x, have horizontal tangent lines? It has horizontal tangent lines at the values of x that have the form pi over 4 plus any whole number multiple of pi. Yeah. So if you add, say, 1 pi, you'd get 5 pi over 4. If you add 2 pi, you'd get 9 pi over 4, and so on. So if we switch back real quick to the Desmos graph, I promised we would, so let me keep my promise. Oh, I'm lost in my own computer. Sorry. Let's see what you're seeing. I don't think it's switched. I don't think it's switched. Sorry about this. I know that it can be frustrating watching these videos under these circumstances, but I also hope you remember that I made this course just for you. But here we go. You should be able to see the Desmos window again. And let me start on this one. If I mouse over this point with that horizontal tangent line, notice the x coordinate. If you can see it, maybe I can make this a little bit easier for you to read. Notice that that x coordinate is pi over 4. Yeah. The next one, 5 pi over 4, that's pi units to the right of it. The next one, 9 pi over 4, that's another pi units. So they happen every pi units. This one, negative 3 pi over 4 is pi units before pi over 4, and so on. Cool. Okay, this video is getting a little long, but I want to do one more hopefully illustrative example, and it will circle back through some of our ideas about position, velocity, and acceleration. All right, so I want to do one more example, kind of physics-based application. This one, I took it straight from your text, so we can save a little time in writing it. So here's what we have. We've got an object, a weight, it looks like, attached to a vertical spring. And then that vertical spring has an equilibrium. So that equilibrium value is right there at x equals 0. So if you let this system come to rest, the spring is going to be hanging at that height. And then in our coordinate system, the positive direction is down and the negative direction is up. So when this spring gets stretched 4 units out of equilibrium, that means it's being pulled down. Yeah. So positive 4 units out of equilibrium is being pulled down out of its rest position, its equilibrium position. And so somebody pulls this thing 4 units down out of equilibrium and then releases it. Okay, releases it from that position. So the downward direction is positive. And one model, this is simplified physics, we're ignoring a lot of things like friction and air resistance and all kinds of other forces, but one model for the position of that thing, kind of in a vacuum, would be given by this function 4 times cosine of t. All right, so what do I mean by that? I mean, if you plug a time value into this expression, then the output of that function tells me where this object is. And that might be a positive or a negative number. And remember, if it's a positive number, then the string is stretched beyond its equilibrium. If it's a negative number, the string is compressed below its equilibrium. All right, so that's what the author means by these signs. Negative means compressed. Positive S means stretched. S equals 0 means it's at rest. And we want to find the velocity and the acceleration and use them to analyze the motion. Okay, well, velocity. Can you answer the question before me, or can you tell me how to compute it? Velocity is the derivative of position, right? Velocity is s prime if s is the position. So here our s is 4 times the cosine of t. So the derivative of it will be 4 times the derivative of cosine of t, which we have derived is negative sine. So our velocity function is negative 4 sine of t. What are our units here in this thing? We're measuring distance in centimeters, and we're measuring time in, does it say it? It should say seconds somewhere. I don't see it anywhere, but I'm going to assume that time is measured in seconds. All right, so the units on this velocity would be centimeters per second. Cool. How about the acceleration? Acceleration is the derivative of velocity, the second derivative of position. Okay, well, the velocity function is -4 times the sine of t, so the acceleration is -4 times the derivative of sine of t, that's cosine of t, and its units would be centimeters per second squared. All right, so there is the velocity and the acceleration of this object at any time t. So that's one thing we were asked to do, find the velocity and acceleration. Okay, we found them at time t. And now what about analyzing the motion? I'm just gonna scroll down. I took the nice graph from your text because it's color coded and drawn very nicely to scale. So can you see the labels on it? The author has labeled the position, it's drawn in red, the velocity, it's drawn in blue, and the acceleration is drawn in green, right? So what are those four curves? Let me just write their formulas down here to remind you that S of t was 4 times the cosine of t. Yeah, it looks like a cosine wave with amplitude 4. V of t was -4 times the sine of t, and A of t was -4 times the cosine of t. Right, so those are the formulas that we derived up there. So what does this mean, analyze the motion? It's a very open-ended question, but I'm just going to kind of hit some highlights here. Well, first of all, this object is going to just oscillate in between s equals 4 and s equals -4. It's going to bounce between, remember, when s is 4, it's stretched 4 centimeters beyond equilibrium. When s is -4, it's compressed 4 centimeters below equilibrium. So it's just bouncing between stretching out to 4, compressing down to well, 4 below equilibrium, -4, and so on. And it's going to do that every 2 pi seconds. It's 2 pi period. So in this physical vacuum, this object will just oscillate indefinitely. Every 2 pi seconds, it returns to its previous position. Right? The speed, I want to remind you, speed is the absolute value of velocity. So that's the absolute value of this function -4 sine t. Well, that would just be 4 times the absolute value of sine of t. Yeah. So one question that you might be interested in is like, well, when is this object moving the fastest? When's its speed greatest? Well, the sine function is greatest. What's the greatest output is 1. So in the interval from 0 to 2 pi, the part that we're looking at here, the sine function will be 1 twice, at pi over 2 and 3 pi over 2. So those are the two times. Pi over 2 is about 1.5 seconds. This 3 pi over 2 is about 4.5 seconds. Those are the two times when the object is moving the fastest. You can see it in the velocity picture here. At pi over 2, the velocity is -4. At 3 pi over 2, the velocity is +4. Both of those have absolute value 4. That's the biggest speed, 4 centimeters per second. And notice that that biggest speed happens when the object is passing through equilibrium. So can you imagine it in this spring system as the spring is stretched, when it's reaches its maximum stretching, 4 centimeters, it turns around and starts compressing as it passes back through equilibrium, passes back through s equals 0, that's when it's going the fastest. Yeah, cool. You can also see the acceleration. It's -4 times the cosine of t. Its maximum in absolute value, I'm ignoring the signs. So the maximum acceleration, the acceleration is the graph that's drawn in green. The maximum acceleration is happening when the spring is kind of at maximum displacement. It's either stretched 4 centimeters outside of equilibrium, the acceleration is maximum, or when the spring is compressed 4 centimeters below equilibrium, the acceleration is maximum. Cool. Notice that when the speed is maximum, when the spring is passing through equilibrium, the acceleration is 0 there. Okay, this video is getting too long. I'm going to stop here. I hope that you'll practice these sines and cosine derivatives, get them into your repertoire. We're going to talk a lot more about equations of motion, so don't worry if this feels like a lot to swallow. I'm just kind of trying to plant seeds. I want to talk about position, velocity, and acceleration throughout this entire course. So this is just one opportunity. There'll be many others. All right, so thanks for listening.